This year's motto is like Montreal Protocol, keeping us food and vaccine cool. But there is another factor we have to look at the success story of Montreal Protocol. This is probably maybe one of the, we can showcase this protocol and its implementation as one of the best practices can be adopted for limiting our global warming to 2 degrees Celsius as set by our Paris Agreement. So there are many lessons to learn from Montreal Protocol and its implementation. At the same time, climate change is not that as simple as ozone problem. That also we should understand. So this is the success story of ozone. This is a satellite image of ozone concentration in the southern hemisphere. So the concentration varies from almost like this is color coded. The color is from mostly from blue to orange. That means the ozone concentration can vary from 200 Dobson unit to something around 350, 400 Dobson unit. So this is the picture in 1979 taken by Tom's satellite. So after that, this satellite based observations of ozone came into effect. So after maybe 35 years, if you look at the current concentration, though this is not updated till 2020, but we can see that the ozone concentration is, this is the level in 1979, something around 200 Dobson unit. So then the ozone concentration decreased over a period and reaches a minimum value somewhere around 2000. Then it is showing a kind of recovery signal. So this is actually the success of implementing Montreal Protocol in 1995. Implementation came in effect in 1995, though it is signed in 1987, and almost like all member states in UN member states, like in 197 countries participated in this. This was the success of this Montreal Protocol that led to the heating of ozone over the years. So when we talk about ozone, most of us, means many laymen we were thinking that ozone is just about blocking the UV radiation coming from the sun. As far as climate scientist like me, I look at this problem in a different way, because there are a lot more things ozone is providing to the climate, or there are a lot of benefits out of ozone we are getting, or our climate is getting. Not only in terms of limiting global warming, ozone is considered as a natural greenhouse gas that is actually maintaining our climate system temperature in a livable range. That is a factor. But other than that, other than the radiational factors like UV radiation or the ultraviolet long wave radiation, terrestrial radiation, greenhouse gas capability, other than that, it is actually controlling our climate system in a stable state by modulating the thermal structure of the atmosphere, and thereby it is making our circulation, the global circulation or the wind system in a stable state and in a livable condition. So that is what the ozone is. Ozone has much more things to do to our climate. So these are I already discussed. So the outline, in essence, what in terms of radiation the ozone is providing to our climate is that this is on this first slide picture on the left side is showing the theoretical solar radiation spectrum reaching at the top of the atmosphere. If you know the black body temperature or the photosphere temperature of the sun, we can derive this, theoretically derive this curve, the distribution of this radiation curve based on Planck's law. We can derive. If you look at the radiation which is reaching at the top of the atmosphere. Top of the atmosphere means the atmosphere covers over a region from from our surface to out to something like 100 kilometers. If you go and measure the radiational spectrum reaching at the top of the atmosphere, you can find that 5% is coming in a UV region, and then 43% in the visible region. Here, this visible region, and near about 52% in the near infrared region. So on the left side, this is what the theoretical curve at the top of the atmosphere is plotted like this. And if we measure the radiation reaching at the surface, we can found that this is the radiation reaching at the top of the atmosphere. That means this curve. And if we measure the radiation reaching at the ground, this will go like this. That means there is a loss of ultraviolet portion of the radiation which is entering to the atmosphere at the top of the atmosphere, which is not able to penetrate the atmosphere and reaches the ground. So this observation led to the invention or discovery of ozone layer. So that by measuring this radiational spectrum at the top of the atmosphere and the surface led to the indication that there is something in between surface and in the top of the atmosphere which is absorbing the radiation in the UV range. So when we talk about ultraviolet radiation, we talk about a uniform thing. Means like ultraviolet radiation, the wavelength of ultraviolet radiation ranges from something like 100 nanometer to 400 nanometer. So based on the destructive capacity, the energy of this UV radiation, we can divide this UV radiation spectrum into three ranges. So that is the UVC radiation, the UVB radiation, and the UVA radiation. So considering the high lower wavelength like 100 to 280 nanometer or higher frequency, their UVC radiations are more energetic. So when it enters at the top of, on the lower side, this is altitude, the height. When it enters the upper atmosphere, the UVC radiation, what it is doing is that it is used to dissociate the molecular oxygen into atomic oxygen. Then, so that most of this UVC radiation will be utilized by this process, and there is only little radiation enters till 30 kilometers in the upper atmosphere. So almost all UVC radiation will be absorbed by this process. When we consider UVB radiation, lesser intensity, but this UVB radiation which is reaching at the top of the atmosphere, almost 85 to 90% is being absorbed in the atmosphere well above the surface. Only 10 to 15% is being reached at the surface. So whatever ozone hole, when we are talking about the ozone hole, any little reduction in the concentration of the ozone in the atmosphere can lead to UVB radiation to reach the surface. So this is what the ozone importance. So then how this ozone is produced in the stratosphere? If you look at the concentration, vertical distribution of the ozone is not a well mixed gas. It is not like our oxygen or nitrogen. If you take unit volume of oxygen from the surface and the unit volume from the upper atmosphere at the top of the atmosphere, it is proportion is like 78% nitrogen and 21% oxygen. But if you measure ozone distribution is not like that. It is not a well mixed gas because it is more active gas, it is always in a reactive mode with both radiation, chemical species and all. It is not a well mixed gas. So if you look at the vertical distribution of the ozone, we can find that the ozone concentration is lower at the surface, then it increases. It is maximum concentration will be found between 20 and 30 kilometers and then decreases. This is the distribution of the ozone, the vertical. So how it is produced is that, as I told, this photo dissociation into atomic oxygen, then this oxygen combined with another O2 molecule to form the ozone molecule. So another reaction is also happening because this ozone is absorbing most of the ultraviolet B radiation, so that it is dissociated into O2 and molecular oxygen and atomic oxygen. Then there is a balance between this is actually this atomic oxygen again can combine with another molecular oxygen to form ozone. So that means the chemical equilibrium, it came to a photochemical equilibrium at a level of this between 20 and 30 kilometers. That's why the concentration is high concentration found here. This is the region where that equilibrium is found. So this entire reaction is known as Chapman reaction. This is about the ozone. But what it is doing by absorbing the radiation is that this is the typical vertical structure of temperature. Temperature, we know that in the troposphere, temperature decreases with the height, then up to tropopause, then temperature increases with height. And if you look at the previous concentration, the ozone concentration also from tropopause, it is increases in the stratosphere and increases and decreases in the mesosphere. Similar to that, the temperature is also decreases in the troposphere, then increases. So that means ozone is playing a bigger role in controlling or making this thermal structure like a troposphere, stratosphere. Why the stratosphere act like a lid to the troposphere? Because if there is imagine if there is no ozone found here, so that means that if there is no ozone means our temperature profile would have been like this. It's constantly decreasing with the height. We know that all our weather features like our cloud system and all, it is happening below 9 kilometers. So this kilometer level, all weather system is happening. If there is no ozone and temperature is not increasing with height, what would have been happened is that this cloud will not be precipitating. It will not rain out. It will go build like that. It can go up to 100 kilometers. It may not lead to rainfall and all. So that means this way the ozone concentration by altering the thermal structure of the atmosphere is actually making the tropospheric weather system to exist only confined in the lower levels of the atmosphere. So that way it has got another thing. And one more thing is that by controlling this thermal structure is driving the wind. So that means the whatever wind field, the circulation we are observing now is, especially in the upper atmosphere, is mainly because of the presence of the ozone. So another factor we have to consider here is that there is good ozone and bad ozone. So always that is another paradox, because in the stratosphere whatever ozone is produced, that is produced through natural factors like photodissociation, then Chapman cycles, and that series of reaction is happening naturally. But in the case of, if you look at the entire ozone concentration in the vertical, almost like 90-95% is confined in the between 20 kilometer and 35 kilometer, almost like 90%. But rest of the 5 to 10% will be available in the lower level, especially in the surface layers. So this ozone which is found in the surface layer is not because of the natural process. It is mainly because of the anthropogenic activities, especially the pollutions, the NOx or volatile organic compounds and other pollutants. So through that photochemical reactions, so in the presence of photochemical reaction, that means the NOx combined with the VOCs will produce ozone in the lower layers of the atmosphere. This ozone, though ozone in the upper layer is considered as or blocking the ultraviolet radiation and maintaining our thermal structure and controlling our global circulation factors, but the ozone which present in the lower level is considered as a toxic gas. That means it can create irritation to the skin, throat, or nervous systems and all. It is considered as a highly pollutant species. So that means the tropospheric ozone is bad ozone, and stratospheric ozone is considered as good ozone. So coming to the discovery of ozone, this is the man, the Dobson. He invented a photospectrometer which can measure the total ozone content. So that means the entire ozone concentration in the vertical column of the atmosphere. With this photometer, he measured. So this is nothing but if you compress the entire ozone present in the vertical column, and if you compress and bring it back to the surface, it will be something like 300 Dobson unit, which is something around 3 mm thickness. So this much small quantity of ozone is only present in our entire atmosphere. So this 300 Dobson unit is something near about 3 mm. So this is invented by Dobson. That is why it is followed by the unit Dobson unit. So that is regarding that is how the total ozone concentration is measured. Otherwise, the vertical distribution and everything is measured as mixing ratio and all. So now coming to the ozone hole, there is a mixed conception that the ozone, when we talk about ozone hole, it is actually not a physical hole that we consider ozone as a umbrella. It is not like a hole on the umbrella. So what is ozone hole? After the invention of this, after the satellite based measurements started, the ozone hole is defined as the area in the or the region where total column ozone concentration will be less than 220 Dobson unit. So this is the scale. So if it is below, if it is in blue shade, means it will be 220 and below. So that means this is how the ozone hole is defined. If the concentration is reduced below, the total ozone concentration is reduced below 220 Dobson unit, then that region can be termed as ozone hole region. So this is the image from Antarctica. That is also a matter because this much bigger and evident ozone hole is not that much prominent over the Arctic region. That means the geography is also playing a role in producing this ozone hole. It is not distributed everywhere over the surface. It is mostly found over the Antarctic region. That means Antarctic region, the regional, that geographic location is also very much important. So this is what the ozone hole is, and then a little bit of history regarding the ozone. So as I told, Fabry and Buisson in 1913 they discovered the ozone gas, and then there is another invention happened in 1922 in terms of CFCs. So when it was invented, it is considered as a magic gas with a lot of potential in our day-to-day life. So that is what it is. It was considered as a great invention in 1928. Then later in 1956, British Antarctic Survey team, they started observing the total ozone at the Antarctic region. So that is the first observatory established in Antarctic region to measure the ozone. And then Molina in 1974, Molina and Sherwood, they first found that in 1974 the CFCs has a potential to destroy the ozone. So that is what the first reporting of ozone, the CFC linked to the ozone destruction, and that was published in 1975. But these two fellows got Nobel Prize after 20 years, like in 1995. So that means it took almost 20 years to realize that this has got immense means this itself has a lot to do with our environment. So then in 1978 onwards, NASA started to measure the ozone with satellite using the TOMS sensors, total ozone monitoring spectrometer. They started observing the ozone with the satellite. So then in around 1984, British Antarctic Survey team like Farman, Gardiner and Shangling, they published a paper describing the real ozone hole, what they found in the Antarctic region through their observatory, British Antarctic Survey observatory data. They first published a paper on the ozone depletion. So we should understand that the NASA also started observing from 1978 onwards, but this was considered as a great miss by NASA satellite. As I told, if you take the normal ozone concentration in the atmosphere, we can consider as like 300 Dobson unit or near about 3 millimeters. So it was that time it was not possible that ozone concentration will come down below 220 Dobson unit. So when that is considered as erroneous data. So NASA satellite sensors retrieval techniques ignored that data as erroneous data. Then later, after reporting this, Farman and Guardian, they reported that there is really physically something is happening in terms of ozone hole and all. Then they realized that, then they went back and analyzed their satellite images and found that yes, that is really happening. And then in 1986, NASA also confirmed that yes, there is a ozone hole is coming out. So that led to around this time only Vienna Convention happened, and that led to the Montreal Protocol implementation. And that is the brief history regarding the ozone, invention of the ozone towards the Montreal Protocol. So this is how the ozone depleting substances, especially the halogens, how the chlorine in the CFCs is dangerous to the ozone, because in the presence of ultraviolet radiation, chlorine atom will get dangerous. So it will break the ozone molecule, then form CLO. So then whenever a free oxygen, which is also naturally present in the stratosphere, that react with the CLO, it can make oxygen molecule and liberate the chlorine atom. So that means in this way, one Cl chlorine will make destroy the ozone. At the same time, it can free. It will end up with a free chlorine. So again, this chlorine can go and break another O3 molecule. So that means this chlorine act as a catalytic way to further destruction of ozone present in the stratosphere. So that means it is considered that this way one chlorine molecule has the potential to destroy almost like as much high as 1 lakh of ozone molecules. So this is how the reaction is happening. So there is a lot more to this, because as I told in the beginning, the ozone hole is more prominent. If you look at this is the polar region of the northern hemisphere. This is Arctic pole and this is Antarctic pole. So if you look at the ozone concentration in the Arctic pole, it is very, the ozone hole is not that much evident. But if you come to Antarctic, this ozone hole is very much evident. So that means that is how the geography is also determining in making this hole. So if you look at the wind structure, this is the difference. The wind structure in the northern hemisphere polar region and the southern hemisphere, we can find that the wind structure is less prominent, and the wind structure over Antarctic region is very much prominent. This wind structure is known as polar vortex. So there is a strong rotating circulation over here. So that means it will prevent the polar air to mix with the other tropical extratropical air mass. So that means whatever entered into this polar vortex will remain there. So this polar vortex will become more prominent during the winter season, and so that is what the temperature is also over the Antarctic is very less as compared to Arctic region. So all these factors, the very low temperature along with strong polar vortex, so that is actually making that is the main significance of why we are observing ozone hole, prominent ozone hole in the Antarctic region. Why? Because is that whatever the chemical pollutants or halogens which is transported, the source is mainly the surface. Mainly the population is more in the tropical region. They will produce all these halogen compounds, so CFCs, HCFCs, HFCs and all. They will eject to the atmosphere and it will carry away to the stratosphere. Then that stratosphere circulation will carry that halogen to the polar region. So when this polar vortex is active in the winter, means whatever the halogens enter into that vortex will remain there. So it will remain there for a long time, and then after the winter, the southern hemisphere spring starting. So that time there is a cloud known as the polar stratospheric cloud. This is a breeding ground for the other compounds like HNO3s and ClO, and all. So that means that will also reside on this polar stratospheric cloud. Then when after the winter again the ultraviolet radiation enter to this clouds, that point onwards this destruction process starting. So that means there are a lot of things. It means if you look at the main sources of this ozone depleting substances, ODS, it is not just about CFCs. Other gases are also there, but if you look at their main sources, you can find it in your room. So wherever you sit, you can find the main source to your immediate vicinity or in nearby seat itself. If you look at the ACs, if you look at the furnitures, if you look at the computers, if you look at the paint cans, the aerosol cans, everything in the vehicles, so and the fire extinguishers, these are considered our day-to-day activity, whatever we are using. Most of this the source of this ozone depleting substance is from our coming from out of our day-to-day appliances like fridge, AC, TV and all. So that means we have to find out some alternatives to this CFCs. That is why mainly the Montreal Protocol came into effect. That in a time-bound manner, we have to phase out, cut down, phase out or ban the CFCs in a time-bound manner, so that the total phase out or the total ban will come into effect over a period of time. So that means whatever commitment most of these nations, either the developing or developed nations, committed to this protocol, it is almost 60% is achieved. Another 30 to 40% remaining to be achieved in another 10 years by 2030. So this is what the timeline is defined, and our previous UN Secretary General, the Kofi Annan, he described this Montreal Protocol as the Montreal Protocol is perhaps the single most successful international agreement to date. So why it happened is that there were immediate replacement for this all ozone depleting gases. That was the main success. And another thing is that the industry also realized, and there were industrial or technological solutions available immediately at a lower cost as a replacement. Now it is coming to natural refrigerants and all. So that is why the Montreal Protocol became a great success. And around 10 years after the Montreal Protocol in 1997, and there is another protocol in Japan, Kyoto, that is Kyoto Protocol, which aims to reduce emission of carbon dioxide, other greenhouse gases to about 5.2% below the benchmark level of 1990 levels by 2012. So this is not achieved yet. So that is what the success of one treaty, one protocol, and failure of another protocol. There are many reasons for that. So that in brief we will discuss. This is how it is implemented in a time-bound manner. Initially it is total phase out of CFCs is implemented, and total phase out by the developed countries. It phased out by 1995, developing countries by 2010. Now you cannot find out any CFCs in any of these appliances. But then hydrochlorofluorocarbon came as the immediate replacement, but still it has also got a little bit of ozone killing potential. But then complete phase out is happen in 2010 by the replacement of HFCs, hydrofluorocarbons. So this is how the success we can measure in another way. So we have computer models which can simulate the scenarios for the future. If on the left side, if we are going with the Montreal Protocol, what would be the scenario of our ozone concentration by 2065? So it is almost like most of the global region is showing ozone concentration of above 300 Dobson unit. So that is what if the situation or scenario where Montreal Protocol is implemented. So when we run the model without implementing, so whatever 1987 level of CFC emission, that there is no cut down or ban on using it, exporting it, whatever it is, but it is continuous as a easy go manner, or the business as usual manner. It would have end up with total destruction of ozone, like over entire global region. So this is in another way. So that means only by 2065 only we are going to achieve this. So another main factor when we consider about the Montreal Protocol is that along with ozone depleting potential, these are considered as a potential greenhouse gases. So if you consider CFCs, the greenhouse gas or the global warming potential is something like 5,000 to 10,000 times more than whatever we are talking nowadays as carbon dioxide. If you consider one carbon dioxide molecule, it will produce against one CFC molecule will produce 10,000 times more warming than a carbon dioxide molecule. So that is the meaning. So that means CFCs has a higher ozone depleting potential as well as higher global warming potential. When we ban the CFCs and replace with HFCs, the ozone depleting potential reduced to 0.01% to 5%, and 0.5, but at the same time the global warming potential reduced something like this is 1 to 50%, this is 60 to 100%. So the global warming potential of this HCFCs also correspondingly reduced to a level of like 100 to 2000 times CO2. So I mean, this much 8,000 times reduction in global warming potential is also achieved. It is considered that the Montreal Protocol indirectly led to the reduction of carbon dioxide equivalents in the atmosphere by about 130 gigaton carbon dioxide. It is nearly around 11 gigaton carbon dioxide per year um, emission. So that means in another way, this way it slightly helped to the Montreal Protocol, slightly helped in achieving the Kyoto Protocol and to limit to some extent the global warming level, or extending the date of means year of warming to further. So that is how the Montreal Protocol indirectly helped in, but the replacement what we are talking about, the entire phasing out of this ozone depleting ODS is with the HFCs, hydrofluorocarbons. They have zero ozone depleting potential, but at the same time it is almost having the same level of global warming potential. So this is realized something later, and that led to the amendment to the Montreal Protocol in 2016, that is known as Kigali Amendment. So in that amendment, along with the HFC, also we are nowadays looking for natural replacement of refrigerants in the place of HFCs. So this is how the present level, how it is varying. This is up to the observation current level. The ozone concentration reducing by 2005 it reached a minimum, and from 2005 onwards it is on a recovery path. It's a road to recovery. Maybe by between 2040 and 2050 it is going back to the previous level, and may take another, maybe by 2065 only it will be recovering fully. Maybe it will take another 40-45 years to fully recover back. So that means it is on the recovery path. And what are the natural consequences of this ozone hole, which already we know, everybody knows, it can have impact the human in terms of skin cancer, premature aging of the skin, increased incidence of eye problem, cataracts, and weakened immune system. So then amphibians, like they are more susceptible to this radiations and all. So they are more there, as the mutation is another problem. More and more this UVB radiation can change the DNA and all, mutate, and there are many other related problems. Then in the ocean also, the phytoplankton, the productivity of the ocean, the plant also get affected, because the photosynthesis capacity will be reduced by the more exposure of UVB radiation. So these are some of the health and ecosystem level implications for ozone hole. So this ocean process, it ultimately, any reduction in the productivity will lead to the disruption of the primary productivity in the ocean, and further it will escalate to the destruction of the marine food web and all. So there are a lot of implications if there is more and more ozone is coming to our surface. So this is already discussed, and yeah, another way, as I consider barred ozone, it can, the ozone at the lower level or ultraviolet radiation can even physically damage the structures and all. So that is also a case. And then coming to this, the today, the treaty is widely considered as one of the greatest environmental success in human history. So we can apply what we learned from this massive success to the challenges we are now facing with global warming. So yeah, one way we can say that we can approach the same way, but global warming or climate change issue is not as simple as the ozone problem. So that is the main challenge we want to face in terms of limiting our global warming below 2-degree level by the end of this century, as we have committed in the Paris Agreement. So it is very challenging problem. So it is not a it is not trivial as ozone hole issue. So the climate change issue is a multifaceted issue. It is a highly complex thing. So in essence, what is global warming is that if enhanced greenhouse gas, what we are emitting with our anthropogenic activity lead to the warming of the Earth atmospheric system. So if you consider this problem in such a way that the main issue with the global warming is that we are emitting carbon dioxide or carbon equivalent, carbon dioxide equivalent gases, greenhouse gases to the atmosphere. The budget nowadays is something like that. Out of the, if you take 10 gigaton of carbon, not the carbon dioxide, it can convert into equivalent carbon dioxide amount. But if you suppose that every year we are emitting 10 gigaton of carbon to the atmosphere, out of that 10 gigaton, almost like 25 to 30% is being absorbed by the ocean through photosynthesis or physical mixing and all, and then another 25% will be absorbed by our terrestrial system like ecosystem or the forest and all. So that means out of the 10 gigaton carbon every year what we are going to dump to the atmosphere, the 50%, 50 to 60% will be absorbed back. Another 4 to 4.5 gigaton will be accumulating every year to the atmosphere. That is what this hockey stick shape carving of this carbon dioxide along with the temperature. So these are concurrent. So that is happening. That is the real issue of global warming. This contribution to this is not just CFC like ozone problem. The contribution is from many factors. So there are many anthropogenic activities connected to this problem. It's very difficult to tackle as simple as ozone problem. So this is another way of deriving the contribution, how human is affecting the. I am not discussing that because not required. And now we are reaching at the because IPCC Intergovernmental Panel on Climate Change, they have just released this month last month the AR6 report, assessment 6 report, which is saying that we are at a warming level of 1.1 degrees Celsius compared to the baseline pre-industrial period of 1850 to 1900. So as compared to the average temperature of 1850 to 1900, we are 1.1 degree warmed. So that is the rate. So that means human influence. It is unequivocally, this report says that human influence has warmed the climate at a rate that is unprecedented in the last 2000 years. So this is the main essence of IPCC report just released, and they are linking the human footprint is very evident in this rise of temperature. So that is what the essence, and the recent changes in the climate are widespread, rapid and intensifying. If you look at the 4.6 billion years of Earth history, Earth might have experienced very drastic changes in the, because that might have led to the evolution of many factors, because our Earth is shaped in such a way that there are a lot of geological scale process or climate process and the biological process happened over the years that might have led to the natural evolution on the Earth climate or the Earth system. So if you consider that level of changes, whatever changes happened over a period of like millions of years, what we have observed, that is happening over a period of 100 years. That is what the rapid meaning, the rapid and intensifying, and which is unprecedented in the last 2000. If you look at the human history, like Homo sapiens, we have just 1.5 or less than 2 lakhs of years of history on the earth. So that means in this history itself, we have never experienced this type of rapid warming in this. We are experiencing glacial, interglacial cycles and all, but at the same time we never experienced this type of rapid warming. That is what happening in the last maybe 30-40 years. So it is indisputable that the human activities are causing the climate change. This report makes it clear that the human footprint is there. So that is actually making extreme climate events like heat waves, heavy rainfall, droughts more frequent and very severe. That means frequent and the climate extreme events are not only getting frequent, it is also getting more severe with this climate change footprint. So that is what, if you look at different aspects of this problem, the CO2 concentration, which we never experience. Now the concentration is like 4.419 parts per million volume. So that Earth never experienced in at least 2 million years. If you look at the sea level rise, which also Earth never experienced in last 3,000 years. And if you look at the Arctic sea ice area, which the lowest level, which we never experienced in 1,000 years. If you look at the glacier retreat, which also unprecedented, and we are not experienced in the last 2,000 years. So this is how the climate is changing, and associated with that, how the different ecosystem and other factors is also changing in response to global warming. This is a very, very challenging problem, and we can simulate or derive future scenarios based on different representative concentration pathways and socio-economic pathways for the future. So that is, the climate model projections are not exactly the predictions, but based on different, we don't know what is going to happen in the future. Maybe some immediate technology will be available to take away all the carbon dioxide from the atmosphere. So anything can happen. So that means it is uncertain. So that means we have to look for the worst case scenario and the best scenario. That means a more sustainably developing pathways, like lesser, we have to limit the emission next year onwards and go for a more sustainable way of living. So that will lead to a that will lead to a stage where the temperature may not exceed 2-degree warming by the end of this century. But even if we continue to emit at this way, or even if we take a middle of the road scenario, we will end up like 2-degree warming maybe in next 2060 or 30-40 years we will achieve that level. So that means there are little carbon dioxide is available in our remaining bucket. If you consider the total budget of this carbon dioxide in the atmosphere, to limit that our global warming below 2 degrees Celsius, there is only 300 to 400 gigaton of carbon dioxide is only available in our budget to emit. So that means, considering the 40 gigaton carbon dioxide emitting every year to the atmosphere, we will achieve that maybe that 1.5 degree warming level by next 10 years, and maybe 2 degree warming level, but by next 2050, between 2050 and 2060. So that means the Paris Agreement, what we have set to limit 2 degree warming level by this century, if we are going in this way, it will not be achieved. So that is the main challenge. So that is what the main problem is. This already I discussed. So can we win the battle? So another, I'm going to stop here. We spend billions of dollars to find life on other planets, and trillions of dollars killing the life on this one. So that means the climate change problem is not as easy as ozone problem. It requires a lot of collaborative effort in all levels, not only at the global level, the local level also is required. Not even local level, individual level also required to limit our global warming issue to certain threshold level, to keep this planet livable for our future generations. So thank you.